These positive and negative electrodes, as well as with the electrolyte, there is a charge exchange within that. Any current which is flowing towards the node is considered to be positive, and which is leaving the node is considered to be negative. What is meant by balancing condition? We are balancing the galvanometer to zero deflection. Hello everyone, I am Vrinda, Faculty of Physics from Vidyashram Pre-University College, Mysuru, welcoming you all to session 5 of chapter 3, and chapter name is Current Electricity. In today's class, we are going to discuss about the last bit of this chapter, that is current electricity. So coming on to the topic called as electrolyte. So here we are talking about electrolytic cell. So electrolytic cell consists of an electrolyte solution. These cells are the one which conducts electricity. Okay, it is a cell. That means it is a source to conduct electricity. This is a liquid cell. That is a liquid source which conducts electricity, which has the presence of the solution called as electrolytic solution. And there are two electrodes. One is positive, another one is negative electrodes. These positive and negative electrodes, as well as with the electrolyte, there is a charge exchange within that. Okay, so these positive and negative electrodes are the one which applies certain potential to the electrolyte. So positive electrode, it carries the positive potential, and negative electrodes carries negative potential. So these two electrodes altogether, it has some power in exchanging the charges with the electrolytic solution. For example, if suppose the current which is flowing through it is said to be zero, that is, there is no flow of current, the circuit is off. When this is a case, what happens to the potential within the electrolytic solution? It remains constant throughout and within the electrodes. So you can just apply the potential difference between two of the electrodes can be given as EMF is equal to positive potential, negative of negative potential. So it becomes positive potential, positive, that is you're adding two potentials, add potential which is due to the positive electrode and negative potential which is due to the negative electrodes are fused together, which forms one EMF. Okay, so this is all about your electrolytic cell. So how do you define your EMF? The EMF means it is nothing but it is defined as the potential difference between what? Positive electrodes as well as negative electrodes. So there are two types of electrodes. One is positive electrodes. The cylindrical like structure is called as electrodes, and the liquid over here is known as electrolyte. So what is meant by EMF? That is electromotive force. This EMF is defined as the potential difference between two electrodes, positive electrodes and negative electrodes of a cell when the cell is in open circuit is the definition for EMF. So what is its SI unit? SI unit is given in terms of volts. Okay. So now it is like we are having cells connected in series. We know that in case of current through a simple circuit, we have a voltage which is given as V is equal to EMF minus I into R. It is a general equation. Okay, this one we will have to keep it in our minds. Okay, so now we are connecting the cells in series. Okay, so suppose if you have a connection and there is two cells over here which is present, one call this as point A and this as point B and this as point C. One cell, this is plus and this is minus. It has got plus and it is minus. EMF is epsilon 1 and here it is epsilon 2. And we have a current which is flowing from C towards A, and that is mentioned in I, and the R1 and R2. Call it as the resistance which is present in certain cells. That is the internal resistance. Clear with this? So now getting on to, after we draw the diagram, what is our next duty? That is to give the description. Consider two cells. with EMF E1 and E2, with the internal resistance R1 and R2, which is connected in series at the points A, B and C. So where exactly your cell 1, that is the first cell, it lies between A and point B, and cell 2, it lies between B and point C. Okay, so we have two cells which are in series. Now we are giving the potential of this cell 1 across the points A and B is given as VAB is given as epsilon 1 minus I and R1 because of this above equation. So VAB is nothing but it is just V. Okay. Again you have another one, that is VBC. VBC, call it as the potential across the cell 2, and it can be given as epsilon 2 minus I and R2. Okay, so we have to get the total potential, call it as VAC. From A to C, what is the total potential? Which is given by V, which is equal to VAC is nothing but VAB plus VBC. You're adding up the potentials of the two cells. So it can be written as, what is VAB? VAB is epsilon 1 I R1 plus epsilon 2 minus I R2. So epsilon 1 plus epsilon 2 is one set, and here we have got V, call this as V. So here minus, take it outside, I, and it is R1 plus R2. Now consider a equivalent cell which is having equivalent EMF as well as equivalent internal resistance. So this concept becomes like V is equal to epsilon, this is we have equivalent condition minus I R EQ. This is equation 1 and this is said to be equation 2. So we know that what is our equation 1 and what is our equation 2. On substituting both, that is in this place of V, we are supposed to substitute this equation, which is equation 2. So now equate 1 and 2, we have it like epsilon equivalent minus I R equivalent is equal to epsilon 1 plus epsilon 2 into minus I into R1 plus R2. So your I and I goes out. So what remains is, for this set of equation we have epsilon set of equation. For REQ we have R1 plus R2. We are equating the EMFs together as well as internal resistance the other side. So we have EMF is equal to E1 plus E2 and we have REQ is equal to R1 plus R2. This is only for cell 1 and cell 2. If there are n number of cells which are connected in series, then it goes up till Rn and this goes up till epsilon n. So this is how the cells which is connected in series has got its EMF as well as internal resistance. So how do you give this? How do you explain the cells are connected in series? Means the equivalent EMF of the cells which are connected in series is equal to sum of the individual EMFs. Okay. Similar goes with internal resistance also. The equivalent internal resistance for the cells which are connected in series is equal to sum of the individual resistance. That is how the cells in series goes along. Okay. So this is all about your cell which is connected in series. Now we are getting into the cell which is connected in parallel condition. So what is the parallel case of the cell? So moving on to the cells in parallel condition, I told you, you will already have to remember what is this potential of the circuit. That is a simple circuit which is connected. So it consists of V is equal to epsilon, that is EMF, minus I into R is the actual condition. Now connect this in case of parallel. Okay, that is A point is there, C point is there. How many points? A, B, C. In case of series. Now we will have to take the center one, that is B point, and you have to pull it up, that is such that it makes a parallel connection. Okay, that is dividing your B point into two. Okay, that is one below the other so that you get the parallel connection. So you have your A point and your B point comes out to be like this and your C point is here. This is the partition of B point and C point is here. So it becomes A. This set is known as B and this is known as C. You can mark this as B and this as B. This is the division of B. Split it up. This is one cell and this is the other cell. One is positive, negative, positive, negative. This has the EMF E1, R1 and this cell will have the EMF E2, R2. And how is the current which is flowing? It is towards this direction. So current divides over here which comes to from this way. So division called as I1. The I1 current itself flows here, call it as I1. Downwards it is I2, so I2 current is flowing. So here also I2 current emerges out to point B and moves out to point A. Remember students, in circuit diagram, the must and should most important thing is the arrow marks in order to represent what is the flow of the current, how does the current flows, because of which we can make out what sign we will have to put. The importance of these arrow markers under the sign. What are the sign conditions what you use, either plus to use or minus to use. All these things are attached with the arrow marks what you give. Suppose if there is no arrow marks, you will not be able to understand how exactly the current is flowing and what is the sign what you are supposed to give. Finally, you will go wrong with the expressions. Clear? Okay. So now this is the parallel connection of the circuit. Okay, so cells are parallelly connected in a circuit. That means what is your potential? How is it given? So how is your potential given? For first of all, it is the description what you'll be talking about. Two cells are connected in parallel at point B and each cell is having EMF of E1 and E2 and its internal resistance consists of R1 as well as R2. This is just a small description. By looking at this diagram, you can just say it. So now it is like you're having this diagram. Having this diagram, you will have to give the potential V is equal to epsilon 1 minus I1 R1. I1 condition has existed now, wherein previously I1 was not there because the current was not dividing. Here the current is dividing, that is why you have got the condition as I1, which is equal to, you can rewrite this as you just want I1 to be there itself. It becomes like epsilon 1 minus V divided by R1. Similarly, you have the condition. Similarly, the condition moves out to be I2 is equal to epsilon 2 minus V divided by R1. Now we will R2 this is. So now we will have to check the total current which is flowing through the circuit in case of the parallel combination. In order to check that, we will have to take current I is equal to I1 plus I2. Substitute, that is these two equations, call it as equation 1. Substitute equation 1 in I1 and I2 place. Okay. So we have this equation given out to be I is equal to, what is I1? It is epsilon 1 minus V divided by R1, and you have I2 as plus epsilon 2 minus V divided by R2. On equating this, we have I is equal to epsilon 1 by R1 minus V by R1 plus epsilon 2 by R2 and minus V divided by R2. This is the step. Next we are having I is equal to, you have epsilon 1 R1, I'll equate this and this together, plus epsilon 2 by R2, and in this equation and in this equation, which is common out, minus V. into 1 by R1 plus 1 by R2. I hope you're clear with these many steps until now, whatever I have done. Now let us go to the next one, that is equal to, we have taking the LCM. Epsilon 1 and R2 plus epsilon 2 R1 divided by, this can be written as R1 into R2 minus of V into, this can be written as R1 plus R2 divided by R1 into R2. This is how it goes. So now we have I is equal to, this is the set of equation what is left with us. Now it's our duty to change, that is we have to interchange it. How will you do that? You can just take your V this way and you can put your I the other side. So it becomes V into, that is minus becomes plus, R1 plus R2 divided by R1 into R2 is equal to, you have this equation as it is, R2 plus epsilon 2 into R1 divided by R1 into R2. This becomes minus I. Plus I, when it goes towards the other hand after equal to, it becomes minus I. So this is a set of equation what you're having. So now it is like, we have to get this set, that is R1 equivalent resistance set, and divide these two equations, that is V is equal to epsilon 1 R2 plus epsilon 2 R1 divided by R1 into R2 minus I. You're dividing throughout, that is this equation by this and I by the same internal resistance. So how do you do that? We just give division part and R1 plus R2 divided by R1 into R2 goes out to for both also. So how is this? I have to split this divided by this and this divided by this. So considering this, we will have to solve, and it is like V is equal to epsilon 1 R2 plus epsilon 2 into R1 divided by R1 into R2. And we have minus of I, and we have got certain things over there, that is the internal resistance. So it becomes like I divided by R1 plus R2, and we have R1 into R2 because we have divided, so the denominator comes up with the numerator, that is I. Here also it turns out to be with R1 plus R2, and here it comes out to be multiplication of R1, R2 by the previous equation. Division, denominator goes to numerator, it becomes that the changes takes place over there, what you actually know. Cancel this with this, so it becomes to be 2 plus epsilon 2 into R1 divided by R1 plus R2, and we have I into R1 into R2 divided by R1 plus R2. So we have this set of equation, call this equation as equation 2. Having this equation, it's like we will have to get the equivalent condition. And what is that equivalent condition? It is like V is equal to epsilon equivalent minus I into R equivalent. Substitute in the equation 2, we have E equivalent minus I into R equivalent is equal to epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2, okay, and minus I into R1 into R2 divided by R1 plus R2. So here it is like equivalent condition is this one, and REQ and R, these many things comes out to be together, and I goes off. So we'll have to, if this is equal to this and this is equal to this, divide E equivalent divided by R equivalent. So equation turns out to be, if suppose this is V, you have got E equivalent dividing R equivalent, you have plus epsilon 2 R1 divided by R1 plus R2 divides R1 into R2 divided by R1 plus R2. This cancels with epsilon 1 R2 plus epsilon 2 R1 divided by R1 into R2. If you take this set of equation first, R2 cancels, so what lies is epsilon 1 R1. If you take this set of equation next, R1 cancels, and what remains is epsilon 2 divided by R2. So this is the final equation of the cell which is connected in parallel in case of its EMF as well as its internal resistance. So I hope you're clear with the cells which is connected in parallel. So now it is the most important concept what we are getting into, that is called as Kirchhoff's law, which is very important. So what does your Kirchhoff's law tells? We have Kirchhoff's law, that is two laws, Kirchhoff's first law as well as Kirchhoff's second law. So what exactly is Kirchhoff's first law? It is also called as junction law, that is junction rule, or it is also called as Kirchhoff's current law. First law or current law or junction rule, wherein Kirchhoff's second law is also known as mesh rule or loop rule or Kirchhoff's voltage law. So in Kirchhoff's first law, that is the junction rule or current law, we talk about only the current. In case of Kirchhoff's second law, that is mesh rule or loop rule or else KVL, that is voltage law, we check out only for its EMF and potentials. So what does your Kirchhoff's first law tell? That is the number of current which meets at the junction, that is algebraic sum of the current which is meeting at the junction is equal to 0. Okay, how many number of current which meets at certain point, it is said to be 0. That is nothing but your Kirchhoff's junction rule. Coming to Kirchhoff's voltage rule, Kirchhoff's voltage rule tells that the sum of, that is algebraic sum of the EMFs potential around the closed network is said to be 0. Within that closed network, whatever EMF is there, whatever potential is there, all its sum is equal to 0. That is your Kirchhoff's first law statement as well as Kirchhoff's second law of statement. So these statements are very important. Having this statement, we are just getting into a concept called as balanced condition of one network. What is that network what we are talking? We are talking about Wheatstone's network. So what exactly is in Wheatstone's network? Wheatstone's network in the sense, here you have point A, B, C as well as D. Okay, so here these A, B, C, D is connected with the help of P, Q, R as well as S resistors, which is given as R1, R2, R3, R4. There are 4 resistors which is connected within the points A, B, C as well as D. Okay, so here we use Kirchhoff's current law as well as Kirchhoff's voltage law. How is that we use? Kirchhoff's current law is mentioned as the current which is meeting at a point. Junction means a point where all the way meet. So all the way meets at point B as well as point D. So at these 2 points, we just write Kirchhoff's current law. At these 2 points, point B as well as point D, we just opt for Kirchhoff's current law and the closed loop, which is the closed loop over here, that is A, B, D, A and B, C, D, B. So this is the closed loop what we are consider. In this loop, we are going to apply KVL called as Kirchhoff's voltage law. So here we are dealing with Wheatstone's network. Why we are having Wheatstone's network? We have to check on the balancing condition. What is meant by a balancing condition? That is the circuit is balanced, that is there is no flow of current at that moment. So there will be no deflection which is shown by the galvanometer which is present over here. It shows 0 deflection, that means no flow of current. We have to get that condition called as balancing conditions of Wheatstone's network, that is in this network. Okay, during this condition, how is the equation given is our duty to be checked, which comes every time. It is a repeated question for 5 marks. So this is very important concept from this chapter. That is statement of Kirchhoff's law as well as its balancing condition. So here Wheatstone's network is the cell is connected to A, B, C and D. That is through A the current is flowing and it reaches, there is a clockwise direction of the current as well as anti-clockwise direction of the current. So here whichever goes it comes like this, whichever goes from here comes like this and meets at one point and it comes back to the negative of the cell. So you have point B node and point D node for which the KCL is applied and the internal loop-like structure where KVL is applied. Kirchhoff's current law can also be called as junction rule or else it can also be called as Kirchhoff's first law or Kirchhoff's current law. Whereas Kirchhoff's second law can be called as Kirchhoff's voltage law, mesh rule as well as loop rule. Okay, so now let us get into balancing condition of Wheatstone network, which is very important for 5 marks. So here we have the set, that is a bridge like a structure network, which is used in order to identify the balancing condition of this network. Okay, so your positive of the cell is connected towards the A, point A, through which the current is flowing and the current splits up. It's like a water pipe. There is a presence of pipe which is connected to 2 other pipes. As the water enters, when it gets any deviation, it moves from that deviation. It doesn't wait for any second or third deviation. Once it gets any deviation, it just splits up. So current I is splitted up towards point B and current I2 is splitted up towards point D. So the splitting of the current has taken place and the arrow marks is like I3 goes up like this and I4 direction is towards point C. Okay. So now first of all we are checking into the Kirchhoff's current law, that is at node B, because we can apply at just junction rule. Current law is nothing but junction rule, right? So we are applying to this junction as well as this junction, but our duty first of all it is to apply only for one junction at a time. So let us apply it at node B. So at node B, that is a junction where exactly the point meets. So this will be, for this we are applying Kirchhoff's current law. So it turns out to be at node B, the one which moves towards the node is positive, the one which is leaving the node is said to be negative. So your I1, IG, I3, these two are the current which meets at the point. So plus I1 minus IG minus I3 becomes I1 minus IG minus I3, equate for I3 is equal to, it is I1 minus IG. So now this is said to be equation 1. Next set is, we are supposed to check at node D. At node D we have I2, IG, I4, all 3 junctions meet at this node D. According to Kirchhoff's current law, it is a sum of the current which is meeting at the junction or leaving away from the junction is equal to 0. That is the condition. According to the statement, we are applying the condition. So I2 is the one which is moving towards D and IG is the one which is moving towards D. I4 is leaving the point D. So it is I2 plus IG minus I4. It becomes I2 plus IG minus I4 is equal to 0. So your I4 becomes I2 plus IG. Call this as equation 2. So here ends our Kirchhoff's current law. Now our duty is to apply the second law, that is Kirchhoff's voltage law. Okay, so it is applying Kirchhoff's voltage law. First you have to take, it is a loop rule. So only one set of loop and another set of loop you are supposed to consider. First I will consider this loop and next I will consider this loop which shows the direction of the current. Okay, and remember, the one which moves clockwise is said to be negative. If the current direction is anti-clockwise, it is said to be positive. That is why we tell the arrow marks are must and should, and this is most important and repeated question for your board exams. So here, applying Kirchhoff's law to A, B, D, A. A, B, D, A mesh here if you are considering, or loop, you have got, what is Ohm's law? V is equal to I into R. So the same, that is Kirchhoff's voltage law talks about something about the voltage, that is V. So you're supposed to take the current as well as the resistance. So this is clockwise, arrow mark, it is clockwise. Since it is arrow is clockwise and here it is clockwise, here it is anti-clockwise, here it is clockwise and here it is anti-clockwise. During this condition, when you're considering only A, B, D, A position, it is minus I1P minus IGG plus I2R. So it is minus I1P minus IGG plus I2R is equal to 0. So this equation can be turned out to be equation 3. Now applying to the mesh BCDB. BCDB mesh. For this, how do you apply? It is like clockwise I3Q, that is minus I3Q plus IGG plus I4C plus I4S. It is minus I3Q plus IGG plus I4S. So it can be written as minus I3Q plus IGG plus I4S is equal to 0. Substitute for I3 and I4 from these two equations, equation 1 and equation 2. Turns out to be minus of I1 minus IG into, what is this? It is Q plus IGG and plus what is I4? It is I2 plus IG into S. It can be written as minus I1Q plus IGQ plus IGG plus I2S plus IGS. Now we are considering, if suppose this is equation 4. We are talking about balancing condition of Wheatstone's network. What is meant by balancing condition? We are balancing the galvanometer to 0 deflection. So it becomes Ig is equal to 0. So this is said to be the balancing condition. Balancing condition of the Wheatstone's bridge. Okay. So here what happens is minus I1, Q remains, IGQ, IGG, IGS cancels out. And here in this section it is IGG which cancels out. So we have in this I1Q plus I2S is equal to 0 because this also cancels out. Okay. Next is we have minus I1P plus I2R is equal to 0. So having this equation first, it will be like I1P is equal to I2R. Call this as equation 5. And you have I1Q is equal to I2S. Call this as equation 6. Divide equation 5 and equation 6. We have P by Q is equal to R by S because I cancels, I2 cancels. So this is the set of equation which gives the balancing condition of Wheatstone's network. So this is all about this derivation. Next we are studying about the potentiometer and its working principle. So what is potentiometer over there? Potentiometer is the instrument or a device which measures the EMF, that is electromotive force of the cell, as well as the potential difference between the 2 points in an electric current. This is why this potentiometer is used. So you can get to know how is the construction actually done in case of the circuit and how is its principle taken place. The fall in potential across the conductor is directly proportional to the length of the wire or the conductor. The fall in potential across the wire is directly proportional to the length of the wire, provided it has got certain area of cross section and a constant current flows through it. This is the principle, that is the working principle of potentiometer, which is very important, which will be asked. What is the principle? Give the principle of working principle of the potentiometer. So in today's class, we have studied regarding the Wheatstone's network, Kirchhoff's current law, voltage law, cells in series, cells in parallel, as well as potentiometer, as well as its working principle. Let us all meet in the next class with the new upcoming sessions. Until then, have a good day. Thank you.